Imagine a car that sees a child chasing a ball into the street. The car stops itself, preventing a tragedy. Imagine a store that always knows which shelves are empty. It restocks items just in time for shoppers. Imagine a camera in a busy train station. It can instantly count the number of people waiting, helping to manage crowds safely. These are not scenes from a distant future. They are real applications happening now. They are possible because of a field called computer vision. It is a science that teaches machines to see and understand our visual world. The people who build these incredible systems are called computer vision researchers. They are the architects of machine sight. The work of a computer vision researcher is structured and methodical. A typical day involves several core tasks: visual, quick montage, code and visualizations on dual monitors. They design methods that can find and label objects within an image. This is a fundamental step for many applications. They spend a lot of time collecting and preparing data, the fuel for models. They then train these models. Training can take hours or even days. After training, they rigorously test the results to see how the system performs. They focus on making the system faster. They focus on making it more efficient. They focus on making it safer for real-world use. The daily routine mixes many activities. A researcher might start their day by writing code. Python is a very common language for this. Data is the absolute foundation of modern computer vision. Models learn to see by looking at thousands or even millions of examples. A researcher's first task is often to gather a large and diverse dataset of images or videos. For a model to learn what a cat is, it needs many pictures, breeds, colors, sizes, poses, environments. The quality of the data directly impacts the quality of the final system. Once the data is collected, it must be labeled. This process is called annotation. Labels tell the model what is important in each image. Draw a box around every object of interest: person, bicycle. This is often painstaking and time-consuming. Incorrect labels can confuse the model and lead to poor performance. Researchers ensure labels are accurate and consistent across the dataset. With good data, training begins, often with a neural network inspired by the human brain. Each labeled image produces a prediction. Errors adjust the network's parameters. Repeat over and over until performance stops improving. Testing uses a separate test set and metrics like accuracy, but numbers alone are not enough. Section 4. Real-world impact. Surveillance systems. One of the most widespread applications of computer vision is in surveillance. Cameras are used to monitor public spaces like airports, city streets, and stadiums. Computer vision can analyze video feeds automatically. Systems can detect specific events, unattended luggage, or sudden large crowds that may indicate emergencies. This helps teams monitor vast areas and respond faster. In a crowded subway station, detecting a fall can trigger immediate alerts to staff and operators, potentially life-saving. But surveillance brings significant privacy concerns. Who has access to the data, and how is it used? Responsible researchers build systems that prioritize privacy, blurring faces, and analyzing only predefined events. They implement safeguards, clear retention rules, and ensure systems are not repurposed beyond intent. A system built to count crowds should not identify individuals. Researchers engage with policymakers and the public to balance safety and freedom. Section 5. Real-world impact. Retail and drones. Computer vision is transforming retail. Stores use it to understand behavior and improve the customer experience. Heat maps reveal which aisles and displays attract attention. Managers optimize layout, placing popular items for easier access. Vision monitors shelves, sending alerts for timely restocking so customers find what they need. At checkout, systems identify items automatically, reducing wait times. In the air, computer vision enables autonomous drones. Cameras act as primary eyes for navigation and tasks. Inspections become safer and faster than sending humans to hazardous spots. Over farms, vision detects crop stress, guiding water and fertilizer for higher yields. Systems must reliably avoid trees, buildings, power lines, even in wind, rain, or low light. Researchers add layers of safety, fusing vision with GPS and LiDAR for robust navigation. While computer vision can do immense good, it also carries risks. Models learn from data. Non-representative data can cause bias and unfair outcomes. Vast visual data reveals habits and relationships. Without protection, it can be misused. Technologies meant for safety can be repurposed for harm. Researchers must anticipate dual use, mitigate with diverse data, fairness testing, privacy-preserving methods, and privacy by default designs. Work with legal, ethics, and policy to prevent harmful applications. No model is perfect. Human oversight is essential, especially in high-stakes situations. Vision systems should augment, not replace, expert judgment. Transparent explanations build trust and reveal strengths and limits. Design for a collaborative loop where humans and machines amplify each other. The future is bright, but responsibility must grow with capability. In the end, computer vision is about people, building safe, fair, and helpful tools for a better, more equitable world.